Good morning, everyone. In the previous class, we were discussing about different kind of latches, and we saw like how we can make the tri-state buffer based latches or the other kind of latches. So we discussed the advantages and disadvantages of different kind of buffers. Okay, so based on the forward path and the feedback path, we decided how we need to place the inverters and the transmission gates so that we can have an equal delay in both the directions, like in the forward bias or in the reverse bias direction. Another kind of the like sequential circuit we can come up with, and that is really very important to understand, like how the sequential circuit is different from the latches or other things. So this is also really very interesting, and we should know the fundamental or the things which that can give a unique feature other than the normal conventional inverter. Okay, so what we'll discuss here, because how we are deciding like any of the circuit is sequential logic or it is the normal one. So the simple difference between the sequential and the normal one is like if there is some feedback path, okay, and then we can say this particular design is a sequential one. Okay, so based on the feedback path we can decide it. Okay, but another thing that we should consider here is like this is not only we have a particular combinational circuit and then we are taking something, there is another block which can act as a feedback. Okay, other than these things, we can have a feedback inside the circuit itself that can provide some feedback property, and that can act as a sequential circuit. Okay, so let me repeat it again what I am saying. The basic feature of the sequential circuit is like if there is some combinational circuit and if there is some feedback path which is separated from the combinational one, and I'm just connecting output of the combinational one through a feedback path and I'm connecting to the input side. Okay, so this is how the sequential circuit works. But the other kind of alternative, other kind of arrangement is also possible. Like inside the circuit itself, we can have a feedback kind of mechanism. And if we have a feedback kind of mechanism, then the circuit can, the single circuit can itself act as a sequential logic circuit, right? So let us try to see what I'm saying here. Here we have a circuit. Just forget about transistor M3 and M6. Okay, so let us first start with the discussion of this M4, M5, M2, and M3. So let us consider if there is no M3 and M6. Okay, in that case, how this circuit will behave. Let us try to see. In that case, we will be having a transistors M4, transistor M5, transistor M2, and transistor M1. If we closely see here, transistor M1 and M2 are in the series and we are providing the same input. Similarly, transistor M4 and M5 are in the series and we are providing the same input to all the transistors here. Okay, so if we see here, if input is equal to 0, in that case, both transistor M4 and M5 will be activated and this VDD will be transferred to this V output. Okay, similarly, if input is equal to 1, in that case, M1 and M2 both will be activated and this V out load capacitance at the output that will be discharged through this transistor M2 and M1. Okay, so if we see from M1 to M4, if we have this port number of 4 transistors, in that case, this circuit again, it will act as an inverter. There is no change in the property. Okay, but the question is, what is the advantage or what kind of differences we will observe if we have provided 2 pull-up transistors in the series and the 2 pull-down transistors in the series. Okay, so the advantage will be effectively the width of the complete pull-up network will increase by double. Okay, there is no change in the length, but the width is going to be doubled. like if I'm considering the M3 and M4 and M5 are of same size, so the effective width of this pull-up network will get doubled. Okay.
Sir,
So,
but M4 और M5 सर सीरीज में आ जाएगा तो सर नेट रेजिस्टेंस तो बढ़ जाएगा ना?
net resistance will increase, yes. On resistance will increase, yes. So, but actually this kind of concept, yeah, I think this is not in our scope, but this kind of concept are known as stacking effect. Okay, so because of the stacking effect, yeah, this is what we call stacking effect, we call it. Okay, so with stacking, what we can do, we can effectively increase the strength of the pull-up network. Okay, so this is what we can do. Yeah, of course, definitely resistance will increase, but yes, so like the charging and discharging time constant will also be increased. Okay, but what it happens, like because of this stacking effect, the leakage, like this is the concept basically which is utilized to reduce the leakage current. Okay, this because this is not in our scope in this particular course, so I'm not teaching about this one, what is the stacking effect, how they are affecting the leakage current. But see, we know that, like suppose I have a two transistors in which is in the series, let us assume like this. So the effective body voltage or the voltage at this node is different than the this voltage. Okay, this is because of the body effect which we have already studied, and because of this body effect, effectively the leakage current which is flowing between the VDD and this V output, that will reduce. Okay, so basically this kind of approaches are utilized to reduce the leakage current. Okay, so I'm just leaving here only because these things we may I may be floating one more course in the low power circuit designing in the next semester, so you can opt that one, and then you will understand what is this concept. Okay, but for now just try to understand, like we have already studied that, like this kind of stacking one, and the effect of body bias on this particular node, that this will change the effective body V or VBS of any of the transistor. Okay, and that will lead to reduce the leakage current. Okay, or threshold voltage change, something like that. Okay, so I'm not going into more detail, but yes, my simple intention was to like suppose if I have connected two transistors which are in the series, these two transistors, and if I have connected the input to both the gates, in that case this circuit will again act as an inverter. Yeah, definitely there will be some more delay, but the less leakage power. Okay, the power dissipation will be less. Okay, but how this power dissipation will be less, we will discuss in the next semester. Okay, now once we are ready with all these four transistors which are simply acting as an inverter. Okay, now what I am doing here, I am just connecting two transistors, one PMOS transistor in between the internal node of these two M4 and M5 and the output, which is this M6, and another transistor M3 which is connected in between the output and the internal node between M1 and M2. Okay, because of this arrangement, these two transistors act as a feedback. Okay, so these two transistors are nothing but these are the feedback transistors which can provide or which can alter the performance of this inverter circuit. Initially, without this M3 and M4, M6, this circuit was completely acting as an inverter. Okay, but what happens if I have included these two things like M6 and M3, there is a feedback mechanism, and now this input is feedback to some of the internal node which can decide the activation of transistors M4, M5 or M3, M2 and M1 based on whatever the logic at V out we have. Okay, so yeah, let us try to discuss each and everything which I am saying here. Okay, basically this M3 and M6 are utilized here to change the device transconductance ratio. Okay, M6 and M3 are basically utilized to change the device transconductance ratio of pull-up network or the pull-down network. Okay, or whatever the circuit I have, device transconductance ratio is, what is the device transconductance ratio? If we try to recall simply, like device transconductance ratio is given by KR, and yeah, let me write it somewhere here so that that can be saved. Okay, so device transconductance ratio is given by KR, and this is the ratio of Kn divided by Kp, where Kn is nothing but this is the mu n Cox. We know that, right? So W by L of n divided by W by mu n mu p. So this is what we call like device transconductance ratio. So basically, this transistor M3 and M6 are utilized to change the device transconductance ratio. Now the question is how they are changing the device transconductance ratio. So let us try to understand what happens. Okay. Basically, if I'm changing, like let us try to see. Suppose I'm changing the input from low to high. Okay. If I'm changing input from low to high, in that case, what will happen? I'm changing this input from low to high. So initially input was 0, and I'm assuming output is equal to 1. Okay. If output is equal to 1, what it means? Initially input is equal to 0, output is equal to 1. This M4 and M5 will be in the on state. Okay. But if you see here, what about the feedback transistors? If the output is equal to 1, this will activate transistor M3. And if this will activate this transistor M3, what it means, this logic will transfer here. So here the Vx voltage, whatever here, that will be something different than what we expected. Okay, so here we have some voltages because it is input. I'm assuming these both the transistors are in off state, but because this is this M3 transistor is in on state, it will provide some voltage over here. So that can change the effective resistance of the path. Okay, so this Kn by Kp ratio will change. How it will change? We will see this in the mathematically. Mathematically, we will see it. Yes.
Sir, how this the logic at Vout will transfer to Vx, because there is oxide layer which cannot like conduct.
No, but oxide layer which cannot conduct. What it means? Simply see here. This logic 1 will activate this transistor, and one other terminal is connected to the VDD. So this VDD high will transfer here, right? So this will activate this node. So because we have provided logic VDD at one of the terminal to this NMOS transistor, that will be connected to this node Vx. Okay, so that will change some of the voltages at node Vx. You got the answer?
Yes, sir. Yes, sir.
Okay, so this will happen, and because of that, so initially we know that the characteristics of the CMOS inverter is something like that. Like if I'm changing the input, so the inverter characteristics is something like this one. Okay, but because if I'm changing the input from low to high, at that time output was 1, and this M3 was activated, this Vx was something higher potential than usual one. So this will change the transconductance. So the the strength of the pull-up network, this pull-up network will be more stronger than this one. Okay, so this strength of this will be more stronger than what it means. We will observe the transconductance, or we will observe the characteristics something like this. Okay, so this is the behavior which we will observe if I'm changing input from 0 to 1. Okay, because here the strength of the pull-up network is more, because this M3 weaken down this pull-down network. Similarly, if I'm changing the input from high to low, okay, from VDD to 0. So initially the input was VDD. So in that case, this output will be 0. And if output is equal to 0, then this will activate this transistor M6. And if this will activate this transistor M6, this ground will be transferred to this Vy. And if the ground is transferred, then in that case, this will weaken this one. This will make more stronger pull down network. And the more stronger pull down network, we know that, like, if I have an inverter, let me explain that thing so that you will be able to understand. Like, suppose I have an inverter. Okay. Something like this, and this is the V input and V output, and let us assume this is the output characteristics. Okay, this is the output characteristics. If I am increasing the strength of pull-up network, then we know that this slope or this characteristics will shift in the right direction. We have already studied this one. If the strength of this PMOS transistor is more, then this characteristics will shift in the right direction. And if the strength of this pull down network is more, then these characteristics will shift in the left direction. Okay, so this is what we know. We already know this, what is the effect of this transconductance ratio, device transconductance ratio on the transfer characteristics. So this we have already studied. Okay, the same kind of concept is working here as well. Because of this feedback path, we are not only changing the size of this one, but by this feedback, we are changing the strength of either pull-up network or the pull-down network. Okay, here what we did, we are simply changing the size of the transistor so that we can make more stronger pull-up network or the more stronger pull-down network. But here we are not changing the size of the transistors, but by connecting the feedback network, we are changing the strength of the pull-up network or the pull-down network. And this is the important thing which we should know. Okay, so in the first case, because the pull-up network is more stronger, so we will be having the behavior something like this one. But if I'm changing the input from high to low, in that case, this M6 will be stronger. So M6 will be in on state. So the pull-down network will be stronger. So the logic high will be for longer time period, right? So the behavior will be something like this one. Okay, and but observe that here we are changing the input from VDD to high, so the direction will be this one. Okay, so the important point to note here is, like, if I'm changing the input from low to high, in that case I will observe this kind of behavior. But if I'm changing the input from high to low, then the behavior will be like these kind of things. And if you see here, we can observe some hysteresis kind of property. Hysteresis property means what? If I'm talking about this simple inverter, if I will change the input from low to high or high to low, both will follow the same path, right? In both the directions. But because of this feedback mechanism, this particular circuit will not provide the same path, but for the both 0 to VDD and VDD to 0, the path will be different because of the different kind of transistors are in activation. Different kind of feedback mechanisms are working. Okay, and because of that, we will observe this kind of behavior. And if we have this kind of behavior, there is some hysteresis property present over here. So this particular width is known as hysteresis width. See, this width is known as hysteresis width, and the points at which we are crossing this one, this point is known as VTH, means higher threshold voltage, and this point is known as VTL. Now, one very important thing. Suppose I have this, let me rough few things because there are a lot of junk here. Okay, so important thing is because we know that the this VTH and VTL depends on this transistor sizing M3, M1, M6, M4, or all the transistor sizing. But if we properly match all the transistors, definitely we can make VTH is equal to VTL. Okay, VTH and VTL, we can make this both the voltages equal by proper optimizing the size of these transistors. But the question is how we will optimize it. Randomly we cannot do, like hit and try method is not applicable over here. Okay, so we need to come up with the expression for VTH and the VTL, and once we are ready with this expression of VTH and VTL, and then by putting some of the values we can calculate VTH and VTL equal, and in that case we can have a characteristics which will be something like this. And at this point this is nothing but here VTH and VTL are equal. Okay, at this point VTH, so this is for the both that direction. Like if we have properly managed, then the direction will in both the direction they will follow the same path. But the question is how we will manage those things, how we will match those things. Okay, so to match those things, let us try to derive the expression for VTH and the VTL. Okay, once we will be ready with the VTH and VTL, then we can come up with some very good things. Yeah, let me. Okay, so yeah, so let us try to discuss more in detail about the VTH and the VTL. Okay, let us try to calculate the VTH first. Yeah, so this is what we have the circuit. Now I'm considering if I have to calculate the VTH, I just explained in the previous slide, like I have to change the input from 0 to 1. Okay, so that I can calculate the VTH. And for VTL calculation, I need to change the input from VDD to ground. Okay, so this is the consideration which we have already done. Okay, so here we have a circuit. Now consider V out is equal to 1. Initially, I'm considering the V out is equal to 1 because the capacitor is charged. And now what I'm doing, I'm changing the input from 0 to 1, because see, initially if I have the 0 input, then the output will be V out. Definitely it will be like that. But now what I am doing, I am just simply changing the input from 0 to VDD. Okay, if we will do something like this, then what will happen? Okay, so if we will keep on increasing this one, so as we know that the characteristics is something like the inverter only, but at the nearby point of the VTH, transistor M1 and M3, these two transistors, because initially the V out was 1. Okay, this V out was 1, which activated this transistor M3. Okay, and at the point when, let me go back to this slide here. If you see here, we know that this is the point where both the transistors are in saturation. This is the same condition like in inverter. Okay, this is the point at which both the like pull-up network and the pull-down transistors are in the saturation region. But because this VTH is decided by the feedback path, how it will act at the nearby point of the VTH, whatever we have. Okay, the transistor M1 and M3 both will come into the saturation region, because this will because of this high, this transistor is activated and this VDD will transfer to this one. So this transistor M1 will get something like some of the expression, because the V in is changing from 0 to 1. So the VGS will be somewhat higher voltage, so it will try to activate this transistor, and there is a potential difference between this node and this node, like Vx and the ground. There's a potential difference between both the terminal of this M1. So this transistor M1 will be in the saturation region. Okay, so if both the transistor M1 and M3 are in the saturation region, in that case simply we need to calculate the expression for the saturation. Okay, so how the expression will look like, simply for the transistor M1 it will be like V in minus VTH. We know that K by 2 VGS minus VTH whole square. This is the simple expression for the saturation current. Okay, so the K1 which is for the transistor M1, and V in is nothing but this is the VGS for transistor 1. Okay, so this is the VGS of transistor 1. So VGS minus VTH whole square, this is the saturation current for transistor M1. Similarly, if we try to calculate the saturation current for transistor M3, then this is nothing but what is it is like here. If we see, VG is initially we calculated like VDD. I have considered VDD, and if we see VS is nothing but this is the VX. So the VGS will be by like VDD minus VX. So this is nothing but this is VGS of 3, VDD minus VX. Okay, and minus VTH whole square. So this is how this expression we can observe. Okay.
Hello, sir.
Yes, please.
Sir, how are we equating currents? Like even M2 will be in on state, right?
M2 will be in on state, but because see here, it will get path like see here, because
VX is VDD, so M2 will be off or
M2 will be
off.
Yeah, see here, this is high. This is also somewhat very close to this one, so there is no that much potential difference. So this we will not consider this one. So the path we will get the path from here only.
Can you repeat again, sir?
Yeah, see here. Initially output was VDD, okay, and VX is nothing but this is like we are passing, because this VDD output will activate this transistor M3, okay, and here we have one terminal is like VDD, and we are passing logic high through NMOS transistor. So this VX is nothing but this will be equal to VDD minus VTH. Okay, there is some threshold voltage drop, which is high potential. And if you see here, this is VDD minus close to VTH. So the potential difference is approximately around VTH only. So this is not in the saturation region. This is in the near threshold voltage region. So this transistor M2 is near threshold one. So this M1 and M3 will be only in the saturation region, not the M2. You got the thing, or I need to repeat it again?
Sir, but it is an active region, right? M2?
See here, we are providing, even though we have provided a somewhat higher potential at VGS. So now try to calculate what is the VGS of this one.
Approximately VTH.
And approximately, see here, I am just increase. No, how approximately VTH?
Sir,
this is the VG.
VDD,
okay, this is the VG, which I am increasing from 0 to somewhere higher, something like that. And this VX is nothing but this is the VDD minus VTH3.
Yes, sir.
Okay, so this is the VS of this transistor M2, and VG is even less than the VDD. So if you see, this will not be in the active region, right?
Okay, sir. Yes, sir. Means it is not. It is transitioning from.
Yes, it is not up to the VDD. It has started transitioning. Like if you go back to the previous slide here, at this point, this input is not completely VDD, and at this point, it is even less than VDD, which is close to mid value. Okay.
Yes, sir. Got it.
So in that case, this transistor, what we said, the M2 will not be in active region, because the VGS, I need to calculate the VGS here, right? VG was around some positive value, but VS is VDD minus VTS, which is very high, and the VGS is not greater than VTS. So in that case, this M2 will not be in on state. Okay, so we will be having only two transistors, M1 and M3, and this M1 and M3 will be in the saturation region, and then we need to equate both the currents which is flowing through M1 and M3. So I have equated something like this. Okay, once we have equated like this, what I need to do, because we know that here this Vx is nothing but this is the this also depends on, like, because this transistor is in on state, so this will activate something. So as this voltage reaches up to like if I will increase this node voltage Vx is reduces if Vn will increase. How? Because this Vn is increasing, so this M2 will start activating, it will start conducting, and this is also in activation region, so both the transistor will comes into the picture. So this Vx will start decreasing because it will get path through this one. So stronger the path will reduce Vx. Okay, so this is the important thing that we should consider here. So as Vin is keep on increasing, this Vx will keep it will start decreasing, and because of that, because this Vx now becomes a function of Vin and of Vth, this transistor M2 will be in the on state once this condition is achieved. Okay, and then in that case the output will switch to logic 0. So until this V2 is not in the on state, initially it was in the off state, what we calculated before. In that case, the behavior is something like that. But once this V2 becomes in the on state, like the potential difference between gate and the source terminal is greater than VTS, this M2 will be in the on state. M1 is already in on state, so it will get this V output will get direct path to discharge through this M2 and M1. Okay, and it will get direct path, so this V output will become 0. Okay, so this is the important thing which we should consider, like V out will become 0 once M2 is in the on state. Once we are getting all these things, just try to substitute all these things. Vx is equal to Vin minus Vth in the expression, and try to solve for the Vth. So you will get the expression something like this. Simply what I have to substitute, I have to substitute like Vin is equal to Vth and solve for the Vth, and you will get the expression something like this. Okay, so I'm just do it. Just we have expression like this, and put this expression, and Vin is equal to Vth, and try to solve for the Vin or the Vth. You will get the same expression what I have written over here. Okay?
Sir,
Yes, please.
why I'll have to submit Vin equal to Vth?
Vin is equal to Vth. Once you just come wherever Vx is there, like put this Vx is here. Okay, and then because the input voltage, like why I'm here, let me see here. If you see here at this particular point, this input voltage is nothing but this is equal to this threshold voltage. Okay, and we are interested to calculate what is the input voltage at which the input and output behaviors are crossing to each other. Okay, so at this point Vin is nothing but this is equal to Vth. If you see here, let me move the pointer. If you see here at this point, Vin is nothing but this is equal to the threshold voltage of the circuit. So that is why we are equating Vin is equal to Vth at this point.
And sir, is there any difference between Vth and Vthn, which you wrote in next slide?
This Vth is the circuit threshold voltage during high to low transition, and Vthn is the transistor threshold voltage.
Okay, sir, can you go next slide?
Yeah, I'm going here. So this Vthn is nothing but this is the threshold voltage of the NMOS transistor. I am just making it different, like Vthn is nothing but this is the threshold voltage of transistor, whereas this Vth is the voltage at which there is switching, where the input and outputs are equal, are at the same point. Okay, so this Vth is different from the threshold voltage of the transistor.
Okay, sir. Sir, one more dot.
Yeah, please.
So like when M2 will be on, so you told that Vot will be discharged through M2 and M1. But yes, there is a path, there was a path before M2 being on through like Vot to M3 and through M1. So
yes.
Like
so
it will discharge previous before M2 being on, right?
Yeah, so what happens, so as we are keep on increasing the V input, right? So this voltage will also change, like this is the function of the threshold voltage and the input voltage. If you see here, this Vx is the function of input voltage and the Vth. So this voltage will become very less, right? So if this Vx voltage will be very high, so the potential difference between this node and this node will be very close to the Vth. let me repeat it again what I'm saying. Let us assume V in becomes VDD. Okay, so this Vx will become VDD minus VTH. So this Vx is equal to VDD minus VTH, and here we have a VDD. So this potential difference, the difference between these two nodes, source and drain, is simply equal to the threshold voltage only. Okay, so this will be very minimum voltage. Okay, so the strength of this M2 will be reduced and M3 will be less. Whereas because the M2 is in on state, this complete logic will be switched from M2 to M1 and to the ground. You got something? Or
and sir, when Vx will be equal to like VDD minus VTH, as you said, 1 point it will be VDD minus VTH, then
yes,
that point also M2 will have very less strength, right? Because V out is VDD.
V out is equal to VDD, yes.
Then at that point also M2 will have very less strength. So like,
yeah, so suddenly once this Vn crosses, so this is the beauty of this Schmitt trigger circuit. Let me go back to this one. If you see here, there is a big fight between M2 and M3. Like M2 tried to pull it like to maintain at the high VDD, and M2 tried to pull down it the voltage one. Okay, but what happens once there is a slight toggle between these two things? Once the input crosses that slight voltage difference, immediately this M2 turn on and this M3 turn off. And that is why we are getting the sharp kind of transition from high to low. And this is the importance of the Schmitt trigger circuit. If we talk about a normal CMOS inverter circuit, the transition is not sharp. But in the Schmitt trigger circuit, because of this feedback mechanism and the activation of this transistor M2, the transition becomes very sharp and suddenly fall can be observed. Okay, so this is the importance. Like there is a huge fight, and once they crosses each other, like this M2 becomes the stronger than this M3, then this will discharge the capacitance immediately. Until then, this M3 will try to keep holding this charge capacitor, the load capacitance at the high logic. But once this M2 is on, it will immediately discharge these things. You got the answer, or I need to explain more?
Sir, like I have one doubt. V out was 1, so V out was VDD, right?
Yes.
And when the Vx changed to VDD minus VTH at the end of transition, right?
Sorry. Vx, you're saying like VDD minus VTH?
At the end of transition.
Okay.
Is it right? Like VDD, Vx will become VDD minus VTH?
Yes,
right?
at some point it will become, but this is not completely true. Let me go back to the next slide. If you see here, this expression, Vx is equal to V in minus VTH. Okay, so this V in, you are saying the extreme value, which is the VDD minus VTH. Okay, and that will be achieved at this point, and the transition is well before this point. Okay, so this Vx can never be like VDD minus VTH, and before that there will be some transition.
Okay, sir. Okay.
So this V in can never, like before that the transition will be there. So just try to keep all these things and then try to understand. In case of any doubt, we will discuss later, no problem. Okay, so this is how we can calculate. Yeah, just make sure that this V in this expression will never reach VDD, and before that the transition will be there. Okay, because if you see the VTH is V capital T and capital H is less than the VTH. Okay, so if we try to solve all these things, we will get the expression something like that. Similarly, if we consider the if we try to calculate the VTL, so similar kind of concept will be utilized. I need to change the input from VDD to 0, and I need to consider the V output is equal to 0. Okay, so I need to consider this V out is equal to 0, and input will change from VDD to ground 1. Okay, and by considering these two things, the same kind of expression like M4 and M5 will be, like M4 and M6 will be in the saturation region, and then I need to equate it, and I need to solve all these things, and I will get the VTL. Okay, so here I'm just showing it, but you can do it at your home because we do not have we have only 8-minute time, and I need to finish 2 more slides. Okay, so I know I want to finish the sequential circuit today only. So just at the nearby point of the VTH, M4 and M6 will be in the saturation region, just like M3 and M1. And we need to equate these two things. And once we are equating these two things, we need to consider some of the equation, like Vy will be is equal to Vin plus VTH. P transistor M5 will be in on state, and then V out will change to VDD. Okay, so the same, just like opposite kind of trend will be there, just like the previous slide. Okay, and after substituting, we will get the expression for VTL. Okay, I request all of you to please go through it again. And in case of any doubt, like while calculating the VTH, VTL, what is the switching, what is the strength of M5, M2, M3, and M6, and how they are deciding the threshold voltage, please go through it. In case of any doubt, definitely we will consider it in the next class. Okay. So this is the way how we can calculate the VTH and the VTL for the Schmitt trigger circuit. Now let us talk about why we need the Schmitt trigger circuit. Schmitt trigger circuits are giving basically the sharp transition, and they can do some transition if there is sufficient change in the input. Okay, so what happens if there is some noise is present in the input which is fluctuating? Okay, so if there is some fluctuating noise present in the input, that Schmitt trigger will not provide the output based on the fluctuation. It will maintain the same logic. So to eliminate the noises, electromagnetic noises, we can utilize this Schmitt trigger circuit. They have some hysteresis width. Okay, we just saw in the previous slide, there are some hysteresis width. And if some noise is present in between these two things, those kind of noises can be avoided. Okay, so if the level of noise is less than this one, then this can treat as the logic high, and if it is more than this one, then it can treat the logic low and high, something like that. But in between, if there is some noise fluctuation, something like this will not be considered, and that will be eliminated. So this is the importance of Schmitt trigger circuit, basically to eliminate the noises. Okay,